Welcome to this video about chapter 6 in Furr's psychometric book, and we're talking more about empirical estimates of reliability. Now, when you look at different ways of estimating reliability, there are three essential differences. One is you have two tests as an example, and you have different versions of the test. Now the reliability is an estimate of the consistency of scores across two versions of the test. Or you have a test-retest situation, right, where you give the test at time 1 and then you give the test at time 2, and reliability is an estimate of consistency of scores across two times of testing. And then we have measures of internal consistency, where reliability is parts of the tests correlating within each other, right? So it's the consistency of scores across parts of the test. So let's talk about parallel test forms and what practical problems might see, right? So if you use two tests and you want to figure out the reliability by computing a correlation between the scores, right? That could give you indication of the reliability, but it's only accurate if the test forms are really parallel. So what does that mean, parallel? It means that the two forms are measuring identical test scores and have the same amount of error variance, right? So in this, if that's true, then the correlation between the two parallel tests is exactly equal to the reliability of the test scores. However, the problem is that we can't really be entirely confident that alternate forms are actually truly parallel. This is because of the fact that no two tests can be certain of meeting the assumptions of the classical test theory of parallel tests. And then in addition to not really knowing if they're truly parallel, there's a practical issue, right? That the tests, even if they're alternate forms, they may not always measure the same psychological construct, right? It might be slightly different. For example, if you have a self-esteem versus, non-social self-esteem, or a socially derived version of self-esteem versus non-social self-esteem. And it also could be that just by the fact of taking the first form, you might already be impacting the underlying characteristics, so that you're already changing whatever you're trying to measure. And that's also referred to as contamination due to repeated testing, right? When you take them simultaneously, there's a potential for the carryover between two tests and the contamination. So therefore the test forms could be, the error scores could be correlated, and then that turns into an issue because, as you remember, classical test theory assumes that the tests are random and error scores are not correlated. So it would mean that those scores would not be truly parallel. So we talked about parallel tests. Let's talk about test-retest reliability, right? And that's, of course, ideal when you have stable psychological contrasts, right? If the psychological construct doesn't change, right? Say, intelligence is assumed to be fixed, or something like extroversion, right? Then you could say, all right, makes sense that we can determine the reliability, right? So between two occasions, and assuming that the underlying construct stays the same, then the correlation between two test scores could be interpreted as an estimate of the reliability of the tests, right? But they also would assume that the two tests meet the criteria to be parallel, right? That is the same test. And if if that's parallel, then we will also assume that the error variance for the first testing is equal to the error variance for the second testing. So there's quite a bit of assumptions here. But let's say if there's something unstable, let's say we're measuring mood states, right? Moods are assumed to fluctuate, right? And now we're trying to do the retest with the two different tests for the mood, right? The variation now that we get between the two tests might be because of the actual change in mood, and not necessarily would not necessarily be an indication of actual reliability, right? So that would then lead to poor estimates of test reliability, and it would defeat our purpose, right? Another thing to think about is when you do a test retest is what's the duration, the time span between the two tests, right? If it's months or years, you might actually have a change in the true scores, which could be really a risk. But if there is too short of a distance, you might have carryover effects between the two tests. So there is really a lot of factors to consider here, and the test retest reliability is therefore really dependent on the assumptions that you have about the stability of the true scores across the test interval. So the internal consistency reliability measures are really an alternative to the parallel tests or the retests, because participants only have to take the test once, which makes it simpler, and you can also apply this to the composite of the test scores, right? So in this case, the different parts of the test are treated as different forms of the test, and it's typically, the internal consistency is typically the most common measure for estimating reliability. And in this approach, there's two things that are major factors to affect reliability. It's the consistency in the observed scores among the different parts of the test, and also the length of the tests. So here, just by the way the formulas work, the longer the test, the more likely it is to produce reliable scores. And we have three well-known approaches for the internal consistency, and we'll talk a little bit more about it. It's the split half approach, the raw alpha approach, and the standardized alpha approach. Okay, so let's talk about the split half estimates for reliability, right? In the split half, we say, all right, we take all our items, we split it in two, and we compare the first part to the second part, right? And we have a formula for that. It's the Spearman-Brown split half formula, which either you have the first part and you correlate it with the second part, or you could also have the odd items correlate with the even items, things like that. For the raw coefficient alpha approach, it really goes back to the item level, right? So each item of the test is looked at like a subtest, and we're then essentially looking at correlations between all of the items between each other, right? Which gives us a covariance matrix for each pair of items, right? And then if you assume that the test then is measuring a single construct, right, then you expect that all the items should first of all covary positively with each other, and then we can add the covariances, the pairwise covariances, and have an estimate of the overall covariance between the items, and we're using a formula to then figure out to express this in a coefficient, and this was named after the gentleman that came up with this, Cronbach's alpha, and this is the most widely used estimate for internal consistency. Then there's also the standardized alpha estimate, and this is closely related to the raw alpha, and it's appropriate when tests or responses are standardized, for example, to convert into z-scores, and therefore you do this before you average or sum up responses. You got to do this when the test items have dramatically different variances, and then you may have to think about standardizing it, and that's so that you don't have if you have huge differences in one particular item in variance, that would affect the overall calculation too much. So by standardizing it, you reduce that weight of that particular big variance, and so the standardization is helping with that. But typically I would try to avoid it though, because the differential weighting shouldn't cause an issue, but it can bias your results as well. Well, so let's say if you have items on different response scales, or when you try to combine scores from different measures, that can create some issues, and you gotta just make a case-to-case decision.